chapter or lecture 5 now, and we're going to be looking at the electric field and what we call continuous charge distribution. So we're going to look at ways that we can be a little bit more flexible with the electric field. Pretty much all we know about how to deal with right now are just point charges. So we're going to try to see if we can deal with other kinds of objects. We're going to try to end up here today with the introduction to the capacitor. And I will sort of say that this is the point, I think, in the course where it starts to heat up. I would say the next couple of lectures, couple of weeks, are going to be pretty intense. It will peak at some point, and it will be, I think, better after that. But so I would definitely put the piece of advice out there is now is not the time to sort of put this off. I would really focus on the next couple of lectures. I really think if you can keep the next couple of lectures together, then the course is going to really work much smoother. So a couple of background pieces. So hopefully you read the chapter or looked at the pre-class videos. So we're going to deal with situations now where it's easier for us to deal with charge as a charge density, which is kind of a hard thing to get your head around at first. And so we're going to do an example here. But so what I mean is the charge. So for what we'll do is for, like, say, some sort of a line of charge, we'll talk about the charge per length. And then in this case, like we're doing here, the area, we'll usually use a sigma, and we'll talk about charge per area. And then eventually we'll get into rho, which is charge per volume. And so, like in this picture here, there's an infinite plane of positive charge. And so what it's easier for us to do is, instead of talking about total charge, right? Well, first of all, total charge of infinite plane, try to talk about that. But the easier way for us to think about it is charge per area. And so here we have an infinite plane of charge, and we're told that the charge density is sigma is equal to 4.5 microcoulombs per meter squared. And so I want to ask you, how much charge is located on a square region of this plane with side 20 centimeters? So give this one a go, make this a pause, and then we'll talk about it. Okay, so again, this is a tricky concept, but basically the idea is that we have this infinite sheet, and I just want to know, okay, how much, if I just make some little, this is supposed to be a square, but whatever, square of charge, or a square of size 20 centimeters, how much charge is in there? And the way we do this is we take this equation and we just invert it. So we say, well, I want to solve for the Q, so Q equals sigma times A. And so again, our sigma here is 4.5 microcoulombs per meter squared, and I want to then multiply by the area. So we're interested right now in just how much charge is located on a square region of side 20 centimeters. So how would I do that? Well, I would just say, first I'd convert it into meters. Those jerks for making that in centimeters. And so it'd be 4.5 microcoulomb, and what will happen is the meters squared will cancel out with that meters squared, and so it's kind of, the units work out to be in charge, just as we expect. And when I did this, I got 1.8 times 10 to the negative second 7 coulombs, which if you look, works out to be 0.18 microcoulombs. So stop here. If this is kind of mixing you up, then I would go back and just read the sort of appropriate section of the text on this one here, just to kind of double check there. Today we're going to continue with our discussion of electric fields, and we're going to talk about something called a continuous charge distribution. And basically that's just some object that isn't a point charge that's charged. So right now, if you've noticed, we can only really deal with point charges, which is a little bit limiting. So we'd like to build our repertoire of things we can talk about. So we're going to discuss this, and we're going to hopefully try to end up with an introduction to the capacitor. So the first thing we're going to deal with in this chapter, which I think is tricky for people. First of all, one thing I should have stopped, just sort of say, I would say the next couple of lectures, maybe the next 2 weeks of lectures, I think are probably the hardest of the whole quarter. All right, and so I really think it's crucial to work hard right now. There will be, I think, you guys let me know, there will be sort of a peak in it, and I think there'll be some sections that are going to be not as quite as bad as the next 2 weeks, but it's really sort of key to work hard now, and I tell you, you'll see that it will get better. And so when we have these large objects, like here we're going to start by looking at an infinite plane of positive charge, it's easier for us to talk about the charge density, which is the charge per some sort of characteristic. And so as an example, there's sort of three classic cases. We use lambda is the charge per length for like a stick of charge or something. We use sigma, which is the charge per area, to be the charge for surface area for an infinite sheet here. So if you have charge spread out in some kind of an area. And then we use rho to be the charge per volume, so charge, that's spread out in some kind of a volume. And so in this particular case here, we have an infinite plane of positive charge, and it has a charge density of what we say 4.5 microcoulombs per meter squared. And I want to know how much charge is located on a square region of this plane with side 20 centimeters. So think about this one, and we'll talk about it in a second here. Maybe pause and try this. This is an important one to make sure you kind of understand, I think, before we move forward. All right, so again, this is one of those ones that I'm going to write out the answer here, and it's the kind of thing that you can say, oh, that's easy, but it really, there's a lot going on here. So basically, if you take this equation and solve it for charge, right, then this becomes not too bad. I put in 4.5 microcoulombs per meter squared. That's the charge density, and then times the area. And so the area, so we're like literally saying, let's just make a little square here, and how much charge is inside that square. And so we got to convert this into meters. And so you'll notice that the meters cancel out, and we're left with just the coulombs. And so when I did this, I got, 0.18, supposed to be a point there, microcoulombs, which is the answer D. And again, the idea here is that there'll be a lot of cases in this section that we're in where we're going to try to, instead of saying this thing has a total amount of charge of Q, we're going to rather, it'll be easier for us when we're doing our math to think about it as how much charge there is per something, okay, which is the charge density. Another thing that's going to be really handy is this sort of idea here. And so here we've got some group of charges, okay, so I've got like three charges. One is a Q, one is a 2Q, and another one is a Q. All right, and so say that we're trying to find the electric field at some point over here. Okay, now what we're going to do is we're going to find different ways to do this. But what happens is sometimes, we've done this before, you'll get some equation, and the thing is you're like, well, is that the right equation? And so one way to check is to take extreme cases. And so here's an example. So suppose we're trying to find the electric field at this point R, and then say we find something. Okay, and so I want to know is, what do we expect the electric field to be if I make R much, much, much bigger than D, where D is the separation between these charges? Okay, so again, I'm not asking you to find the exact electric field here. I'm trying to find sort of the approximation when R is really, really big. So think about this, and we'll talk about it in a second. Okay. Hopefully you got this answer here. And so what does this mean? So let's just go through this. So basically, when I'm really far away, okay, I don't notice this distance D between them. And what I notice is just a really big point charge of 4Q. Okay? Because when I'm really, really far away, I'm not going to notice the subtleties that there's this distance D there. And so what is our electric field from a point charge? Well, it's KQ over R squared. So our distance would be the R squared, and then our Q here would be 4 times Q. All right. Now the other thing is, this is an example which we're going to start doing a little bit more, where we use that K constant as this 1 over 4 pi, and I should clean this up a little bit, epsilon naught. So again, it's just a little bit more of a complicated way to write that constant. But the point is when we go through and do some of our calculations, we'll get some answer, and you might not be able to sort of look at it and sort of think, is this correct or not? But what you can do is check the extreme cases, and if your equation gives you what you expect for the extreme cases, then that gives you a little bit more confidence about it. So what we're doing today is we're going to be treating some object as if it was a bunch of little tiny point charges. All right, so that's going to be the name of the game today. And the way you do that is with this equation here. So So again, we're going to use this law of superposition. Superposition says that, if we have 1, 2, or 3 charges, we just add up the electric field from those charges. But now we're going to take some object, maybe a sphere or whatever. We're going to do a whole bunch of different objects, and say we're trying to find the electric field at some point P. I'm going to break this object into little tiny pieces that we're going to call dq. Okay, so a little differential piece of charge, and then I'm going to find the electric field from that little piece. All right, and then what I'm going to do is I'm going to add all those up, sum them up. All right, you can imagine that if I took this point charge here, or this sphere, I could break it into a bunch of little pieces, and then sort of just add up our electric field from a point charge. Now the thing is because we're doing this in a calculus class, what we can do is then just say that, okay, whenever I have a sum, so here I'm just summing up the electric field from little tiny pieces of things that we're imagining are a point charge. What we end up doing is sort of writing out something kind of like this here. So we're going to turn this into an integral. All right, and what we're going to find is, the way I like to kind of think about it is, I just like to sort of take, what is my equation for the electric field and just make it into a differential. Okay, so my equation for the electric field, we've been dealing with that. I think we're getting pretty good at doing that. Okay, and again, I like this sort of business of writing it out and sort of thinking about it as an absolute value. So what we're going to do, and we're going to go through some examples, is we're going to take one of these pictures and then try to represent this thing here. Okay, if you get really good at sort of writing this thing out, then you can do one of these integrations. And again, this is what I think is really hard, because we're doing physics, and so up to this point we sort of had physics and calculus, and especially with integrals, we haven't really done that many integrals, and so now we're bringing those two together, and using calculus as a tool can be really tricky. Okay, but let's go through and do some examples here. And so our first example is that we're going to try to find the electric field on the axis of a charged ring. So here's our picture. Okay, and so a little bit of definitions. We got a charged ring of radius a, and I'm trying to find the electric field at some point P that's a distance, it's on the x-axis, so it's x away from the center. So we're going to find that we can only really, we can do these integrals analytically only for really cases that have a lot of symmetry. I mean, the good news is we'll find that there'll be a lot of use in the examples that we find, but in theory, you could do this with a computer for any shape. You could take like find the electric field of my face covered with charge all over it at some point P in front of me. You can do this with a computer, where you literally add up the electric field for every little tiny charge or something. So you could do this in theory for anything, but it'll only work out well or nicely, again, our class for situations with a lot of symmetry. And again, sort of the first step in doing this is establishing what your dq is. And so here you see in this picture, they sort of shade in a little region there and say, well, that's my little dq. And so what your first thing is you want to do is you want to try to find the electric field that's coming from that little piece of dq. And for me, again, the way I like to do this is it's find the absolute value of my differential of my electric field. And so it's just like the stuff we've been doing. It's just that you've got to say, okay, so instead of finding my electric field, I'm finding a little tiny piece, the little differential of my electric field, and then it's from a little tiny piece of charge. And so you look here, and so let's look at this equation here. And so dE on my picture, so again, let's focus on this guy here. So I'm doing this dQ, and then this dE over here. All right, and so when I do that, so I'm finding again the absolute value of dE. We'll start thinking about the vector parts of it in a second. Okay, so I'm going to say here's my constant K. Okay, my source is that dQ, and what's the distance? Well, if you look here, right, it's just a little right triangle. Hopefully that makes sense. So you're going to use a lot of right triangles and things when doing these examples. And so the way we defined this is we called, this end of it is the x, this is the a, and then that would make my hypotenuse, right? X squared plus a squared, and the square root of that would be my r. And so when the downstairs part over here would be x squared plus a squared. All right, so I set that up, and that's not that different than things we've done before. And again, that would be this arrow right over here represented by this dE. And so now let's think what we need to do now. Okay, so we need to do a little bit of thinking like we've done before. And so what I'm going to use to my advantage is the fact that there's another dq. For every dq, there's one on the other side that's pointed, in this picture, like sort of that way. And if you look at this picture, hopefully you can, we've seen pictures like this before, where basically what's going to happen is the y parts of these d electric field, DEs, are going to cancel, and the x part is going to double up. And that's going to be our key. And so if I draw this picture that we sort of drew already, it's a little bit bigger so we can see it. So here's my angle theta, here's the x, here's the a, there's my hypotenuse. Now the way this is going to work is, so again, if I'm thinking about this guy here being my dq point charge, then this is my dE, and I can think about there's going to be an x and a y component. And I'm not even going to worry about the y component, because why even worry about something that you know is going to cancel? And so I want to, now that I'm sort of realizing this, find my differential element in the x direction, because that's going to be sort of the key to me. And hopefully you can see that what that would be is it would be the magnitude of our electric field over here. So k dq over x squared plus a squared times cosine of the angle. And so if you look here, this thing that we've called theta here is going to be the same angle over here. Now this is the key point, right? And in a lot of cases, in fact, I would say most cases, it's not actually the integration that gets us. It's the setting up of this business here. Most of the time, the integral will be something that you've probably done in calculus and probably done way harder. But this is really the hard part, is making all this geometry. And again, it's one of those things where you're off by one little thing, it can kind of wreck everything. But so I would stop here and make sure this makes sense, that basically that angle and that angle are the same, and that the DEX would be times the cosine theta. Now the thing is we're going to end up trying to integrate over some variable, and so that isn't theta usually, and so we're going to try to go through and sort of take this and get rid of that theta. It's usually best just to do that and sort of see what you're left with. In this case, so my theta, now again, so I'll write up what my hypotenuse here is x squared plus a squared. We do one of these things where when I want to write out my cosine theta, I'm going to write it as adjacent, which is x, over a hypotenuse, which is that thing. So I get this business here, x squared plus a squared, and of course this is the square root. And just like we've done before, I can sort of, so I'll pull the x over here, and then I'll do this business where we get kind of fancy and put the x squared plus a squared together to the 3/2 power. Okay, and so what that is, again, is that's my DEX from one of these pieces, right? From just sort of one of my three pieces. All right, let's move on. So then, the way we kind of think about it is the total electric field in the x direction from this sphere is going to be the integral over this DEX that we just calculated. And so the DEX that we just calculated was something kind of like this. So kx dq over x squared plus a squared to the 3/2 power. So we're going to integrate over this dq. Now typically it's going to be, or almost always it's going to be better for us to integrate over some kind of a distance. And so what we do is we set up something like this. So we say dq is equal to sigma times ds, where sigma again is our charge divided by length. And in our particular case, so again we generally say that this ring or whatever we're talking about has a total charge q, and so here the sigma would be q divided by the length of the ring, which would be 2 pi times a. And so that would be our charge density. It's q divided by 2 pi a. And so this gives us something to actually integrate over. And so I can plug that in over here. And now we're basically ready to go through and try to actually start doing this. And this is a nice example. So you look at this here. And so what this means is I'm going to be integrating, starting at some point and integrating around the circle, basically adding up the contribution of every little tiny piece of charge. And every little tiny piece of charge gives this much of a contribution to the EX. And what's really nice is that if you look here, as I do that, the X and the A are constants. And so in this particular problem, I can pull everything out. As I'm integrating, my x stays the same, my a stays the same, everything stays the same. And so I can pull all of this stuff outside of the integral. And I just have my integral being over ds. And basically what I'm doing is I sort of pick one point on my ds and I integrate all the way to 2 pi times a. So if I sort of start here, I integrate all around in the circle, so I'm going to add up all the little tiny pieces and go from 0 to 2 pi a the way we've defined it. And so in this case, this is pretty, basically that's the simplest integral we can have. It's just going to equal basically the antiderivative. If I do this here, it would be so kx, all this business here, over x squared plus a squared to the 3/2 power. And so it's just going to be s evaluated from 0 to 2 pi a. And so when I'm all said and done, I'm going to have kx lambda 2 pi a all over x squared plus a squared to the 3/2 power. And of course, you can see from over here, if I just invert this equation, q, the total q of my ring, is just going to be lambda times 2 pi a. And so basically over here can give me a q. And so let's look at this all together now. What I'm saying then is that my electric field total in the x direction is going to be kx times the total q over x squared plus a squared to the 3/2 power. All right, so that's my result. So let's just stop and think about this. So first of all, number one, it is conceivable that we want you to sort of be able to do this procedure. Okay, I think doing the procedure is really hard, one of the hardest things we're going to do this whole quarter, but it is conceivable that we want you to do that. But by the same token, another thing is it gives us another tool in our arsenal to calculate electric fields. So now I could give you a problem and say, here's the electric field of a ring. You can look up this equation and sort of find the electric field right away. Okay, so it's sort of two different goals here. Now, the other thing we want to do is, like I was saying before, is we got this equation here, and it kind of seems okay, but I don't know. And so what we can do is check our extreme cases. And so let's check when x is much, much bigger than a. So what happens there? Well, when x is much, much bigger than a, this electric field in the x direction, right, is going to be, on the top will just be kx q, and on the bottom, basically that means we can just kind of forget about the a. And so we have one of these deals, x squared to the 3/2 power, which of course, what does that give us? It gives us kxq over x to the third. Well, here the x's cancel, and I have kx over x squared. Now, it's not exactly the same letters and everything, but it's the same principle, right? So we would expect that really, really far away from this ring, you can't tell that it's a ring. You just know that it's a little tiny point. And so our electric field of a point charge is kq over r squared. Well, our total charge of the ring is q, and the total distance away would be that x. And so this is what we expect. And so this is the kind of thing that it's really important to do. It's a really good skill to do after you do some big calculation like this, is to go back and check, is what I have reasonable? If you did this extreme case and it wasn't what you expected, then it's a really good indication that maybe you made a little goof somewhere. Now, the next example I want to look at is what's called the electric field from an infinite plane. And this is what we're going to use as our basis, like I talked about last time, is when we're looking at a capacitor. And so in your book, they calculate the electric field from a disk of charge, and it looks like this here. And so what we can do is, just like we did last time, is say, okay, let's look at an extreme case, but kind of a different one. So let's look now what happens. And so again, this is something that you can do with integrals and such. If x is really, really, really small compared to the radius, and so so it's sort of like I'm looking at a point really, really close, and so I'm so close to this disk of charge that it seems infinite to me. Like I can't really see the end. All right, and so if I do that, Okay, and we should just be careful. So just if you look here on this equation, the x is your distance on the x-axis, r is your radius, and sigma is our charge density for a surface, which is the total charge divided by the area. That's what that sigma is. And then k is our old friend, the k constant. All right. And so if I look at this, so if I'm trying to find if I'm really, really super close to that disk, x is much, much less than r, then the equation I get would be, okay, so it's the 2 pi, the k, and the sigma aren't affected by getting closer. But this stuff inside here is, and I have 1 minus, and so I get x over, now here, if x is super, super, super small compared to r, then I'm just going to end up with x over r. Again, this is approximate, like that. And so if x is really, really, really tiny, I can just get rid of that completely, which gives me the approximate answer that the field from the infinite plane is 2 pi k times sigma. Now, what we'll often do here, it doesn't really matter, but the standard way people like to write this is to plug in for that k constant. And so if you plug that in, so it's 2 pi 1 over 4 pi epsilon naught sigma, and you get sigma over 2 epsilon naught. So basically, people generally will express this constant, this either k or epsilon naught, in the way that basically just makes it look prettier. Okay, so I think, you know, most people think sigma over 2 epsilon naught is easier to write than 2 pi. You know, it's basically how many pi's can I get rid of. And so this is the electric field from an infinite plate, right? And that's going to be really key to us because we're going to view a capacitor as 2 infinite plates next to each other. And this is the really tricky thing. We're going to spend some time just kind of talking about this. This thing here claims that the electric field from an infinite plate is constant. Okay, and so basically part of this is that we don't ever see infinite plates, and that whole idea of an infinite plate is kind of a weird thing, right? But that's what we're saying, is that if the plate truly is infinite, if you're so close to it that basically you can't even sort of see the endpoints, then it doesn't matter how close you are to it. Okay, the electric field is the same, and that's a really weird idea. And let's just, again, emphasize that this is the electric field that we're talking about. So I think this takes just a couple of days for most people just to kind of get into their head. And so let's kind of look at that. So again, just to stress that the field from an infinite plate, well, we can sort of say is equal to sigma over 2 epsilon naught. And it works just like a regular electric field. If the plate is positive, the field points away from it. If the plate is negative, the field points towards it. Again, just like our typical ones would be. But the idea is that it does not depend on distance, which again is really weird. And then just so you know, you can look this up, right? This is definitely the kind of thing I would never ask you guys to know off the top of your head. But here's this epsilon naught constant. It looks like this here. Again, the kind of thing you'd always be able to find. And so let's just use this in a clicker question. So here we have 2 infinite plates, a big positive and a big negative. So again, assume that they're infinite. And what happens is I release, a small negative object, so like an electron or something, in the middle of this capacitor. The object will move to the left, right? It's going to be attracted to the positive side and repelled by the negative side. But what description about its actual motion is correct? So A, B, or C. So this is an important one. Stop here and really think about this one, and we'll talk about it in a second. Okay, so hopefully you got this. And so what's going on here? Well, let's go through and look here. So I'm going to call this plate 1 and this plate 2. And so if I look at the electric field right in the middle here, the way it should work is there should be electric field from plate 1 pointing that way and an electric field from plate 2 pointing that way. And so what this means is these are 2 plates with electric fields. Okay, and so what we generally do is we generally say sigma is the charge density of this plate. So we'll call it maybe sigma 1, and this is sigma 2 is the charge density of this plate. And so the electric field total at that point, if I think about sort of like the absolute value, is going to be sigma 1 over 2 epsilon from the one guy plus sigma 2 times 2 epsilon from the other guy. But the key is that these are both constant, and it doesn't matter that I'm at the center. Okay, this problem would be the same if I started over here or if I started over here. At any point inside this place, which is between two infinite sheets, the electric field is constant. And we know one of our definitions here is that force is equal to the charge times your electric field, right? And so if we release some charge there, the force, if the electric field is constant and the charge is constant, the force has to be constant, right? And then we know from 2a that F is equal to ma. So if our force is constant, we're going to have constant acceleration. So really what we're saying here is that inside these two plates, right, we're going to have a constant electric field, which in this case means a constant force, which is going to lead us to constant acceleration for our particle. So it really, again, comes from this idea of the fact that there's going to be a constant electric field. And like I said, it's really tricky to get your head around this idea that basically the distance from this plate does not affect the electric field. And so let's look here. I'm going to try to show an analogy to kind of explain this conceptually, but again, it's really hard to get your head around. So here's our infinite sheet, right? So we've got our infinite sheet here, and what I'm going to do is I'm going to draw a picture in the next slide where we're sort of looking straight down the infinite sheet. So you got to be careful that we're sort of looking straight down it. So in a sense, when I'm looking straight down it, I'm going to sort of make it sort of lose one of its dimensions. Okay, but that's what I want to do. So here I'm staring down, so that ring of positives there is this infinite sheet that I'm staring down. So you can kind of imagine that it extends out and goes through us, and it extends back and goes back from the computer. And I want to look at two different points here, again, just to kind of sort of show what's going on with this infinite plate business. Okay, so I'm going to look at sort of three different pieces of charges. And this is one of those things where you can kind of think of these guys as being like a little DQ. These three charges are like little DQs. Okay, and so we're going to sort of look at how they impact. So again, in this problem, we're saying that if I'm at point A or at point B, relative to an infinite sheet, the electric field stays the same. And so what we can do is look at, I think what most of us want to do is look at this charge number 2 here. Okay, this charge number 2, again, if I think of it as a DQ, okay, obviously, if I'm further from that charge, okay, at point B, it's going to be a smaller electric field, right? But what we're forgetting about is that with an infinite sheet, there's always going to be some charge over here that has this particular behavior that we're going to talk about now, which looks like this. If I look at the electric field from E3 and E1 at the part where I'm really close to the sheet, right, they have very little impact. They essentially are flat, and they mostly cancel out. They push a little bit up, but not very much. But if I look at the electric field from E3 and E1, in this case here, and again, the way you could sort of draw these vectors is sort of, I'm connecting these points here. Okay, something like that, right? And so now there's this much more noticeable push up from those two endpoints. Again, this part would cancel, but there's a much more noticeable push up. And the way that it works is that push up is exactly enough to make the total electric field at B, okay, so if the total is something kind of like that maybe, then it's the exact same as the total from that one over there. And again, this is an infinite sheet, so you can kind of imagine that there's sort of a piece of charge where you are, and also one on the other side of the computer that's having sort of this same effect in the other direction, if that makes any sense. So if I was to say, well, here's my, so this is the picture we're looking at is sort of X and Y, and then maybe the Z direction is pointing at us, right? So there's another sort of a piece of charge where you are watching this, and a piece of charge behind the screen that are sort of making these, that are making sort of electric fields like this, sort of in this, again, in this Y direction where the Z part would cancel. And so basically all around on this infinite sphere, this is happening. So all these little pieces, and it just works out that they exactly add up so that the electric field is the same as long as this is infinite. And of course, at some point you'll get high enough in a real plate where there isn't this extra piece. But in an infinite plate, the higher I go, there's going to be a point like 1 and 3 that are now going to sort of have more of an effect. And so it's as you get higher, you sort of see more of this infinite plate, and it has more of an effect on you. Now, we're going to do more discussions of this. This is going to be a really important concept for us, this concept of the infinite sheet and the capacitor. We're also, when we do Gauss's law, going to find another way to sort of prove this to ourselves. So this, what I did here, is a very kind of hand-wavy way, but I just wanted to kind of give you some kind of a feel for this because it's tricky. Okay, and so let's move on to one final example. All right, so this is the one that I'm going to want you guys to work on, and we'll talk about during active time. And so what this is this is a line of charge with length L, and what we're trying to find is the electric field at point Y. And if you sort of put in some pieces there, so again, you know, what I like to do is try to say, okay, I'm going to find my differential element of the electric field, which is K dq over R squared. So here's my R, my dq is over here, and then just like last time, okay, we're going to be able to represent the total. So the total charge of this line of charge is Q, but we're going to use a density will be sort of more helpful. So this lambda will equal Q divided by L. And hopefully you can kind of see that what we're going to end up doing is the total electric field of this thing will be pushing up in the Y direction, okay, because of the symmetry. Basically, the parts that are in the X direction, you know, again, we're sort of assuming one of these deals, where X and Y, the X parts will cancel. So the question I'm going to give you guys, so I want you to kind of work on this before active time. This is a hard one, so we'll probably spend a good part of active time talking about it this week. But what I want you to do is, this will be your PCQ here. They say, okay, so at the dot, the Y component of the electric field due to the shaded region of the charge is what? Okay, and so so basically what we're asking here is for you to find, so this is the DE, and so like in the last example, I want you to find the DE that's in the Y direction. And we've given you all, with the picture, all the different pieces of the geometry, and so I want you to go through and try to figure out which one of those it is, and then if you get that, that's great. You know, try to keep going and figure this out, but again, we're going to talk about it in active time. And like I said, this is a really hard one. This might be, this is probably in the top, definitely the top 5 of the hardest things we're going to do this quarter. So this is a tricky one. All right. Thanks.